Hello, everyone. My name is Marshall McCall. I'm an astronomer and senior scholar at York University in Toronto, Canada. I'm going to show you how to make a galaxy in the comfort of your home. I will start by talking about what a galaxy is and where it comes from. Then I will go over its constituents and exchanges among them. After that, I will introduce you to a model of galaxy evolution and its predictions by creating a rendition of a galaxy on my dining room table and making it evolve right before your eyes. First, the background. You may know that we live in a galaxy called the Milky Way, one of trillions in our universe. So what is a galaxy? Here is a picture of one. It is a huge collection of normal matter in the form of stars plus gas between the stars, all embedded in a halo of an unseen gravitating substance that we call dark matter. The gravity of everything acting on everything else holds it together. But how a galaxy like ours came to be the way it is now, and how it continues to change with time, is driven by the interactions between gas and stars. The dark matter just sits idly by. You might think that the evolution of something as complicated as a galaxy can't possibly be fathomed. What we astronomers do is focus on the bare essentials. Let's first review the circumstances that led up to the formation of galaxies. Before doing so, it is important to understand that most of the matter in the universe is dark. Only a sixth of the matter is manifested as normal particles like those of which we are made. Here is a simulation that shows how the organization of the dark matter in the universe changed with time. Early on, the dark matter was spread everywhere, but with small undulations in density. As time progressed, gravity caused the dark matter to pool in regions where the density was enhanced. Normal matter, which was mixed into this sea, took the form of a gas composed of atoms of hydrogen, helium, and a tiny bit of lithium. The gas followed the dark matter. Clumps of dark and normal matter grew, larger ones becoming the precursors of galaxies. Now let's focus on a clump to see what happened next. The gas settled into the middle of the dark matter halo. Knots developed in the gas and became gravitationally unstable. The knots collapsed under their own weight, and the first generation of stars was born. Now the clump could be called a galaxy. Normally, many different kinds of stars are born in a generation. However, it is informative to classify them in only two ways. Heavy stars, which by astronomical standards die pretty much immediately after birth, and light stars like our Sun, the great majority of stars in fact, which live so long that we can approximate them as never dying. Each heavy star dies catastrophically. When it burns up its fuel, it explodes as a supernova. So, shortly after birth, the heavy stars expelled their contents at high speed, partially replenishing the gas of the clump. Out of this gas, a second generation of stars was born. The heavy ones exploded. Some of the gas was replenished. From that gas, a third generation of stars was born. And so on, the cycle of birth and death continued to the present, with more and more of the gas being converted into long-lived stars. Today, the galaxy consists of gas interspersed with stars of various masses and ages, all embedded in a huge halo of dark matter. Let's see what happens more tangibly by mimicking a clump. Imagine that the air all around is a halo of dark matter. I will use water to represent the normal matter in the clump. This jug will hold the gas. These glasses will hold the stars. In reality, of course, stars and gas are mixed together. There is a glass for each generation of stars to be born. Notice that the jug is full of clear water and that the glasses are empty. That is because at the beginning, all of the normal matter in the clump is gaseous, essentially just hydrogen and helium. No stars have been born yet. Now imagine that some knots develop in the gas and subsequently collapse under their own weight. The first generation of stars is born. So I have to pour some of the water out of the jug into one of the glasses. Some of the stars are heavy, Boom! They just exploded. They return their contents to the gas. So I have to pour some of the water out of the glass into the jug. But with a difference. During the life of a heavy star, big atoms that we know and love, like oxygen and silicon and iron, are synthesized from some of the hydrogen and helium that the star started with. The matter that is returned to the gas is enriched with such nutrients. So in addition to what I have already poured back into the jug, I have to add nutrients. Jello! Because the return matter is moving so fast, it rapidly spreads out and mixes in. And I'll make that happen with my cosmic stirring rod. Now imagine that more knots develop, this time in enriched gas. A second generation of stars is born. Perhaps with planets around them, thanks to the nutrients. Boom! Some of the stars just exploded, the heavy ones. So I have to return some of the water out of my glass back to the jug. But enriched further with nutrients because yet more big atoms were synthesized by the stars during their lives. The return matter rapidly mixes in. More stars are born, with planets around them probably. It's a third generation, and it's made from gas that is more enriched with nutrients than ever before. Boom! The heavy ones die, returning their contents, including yet more nutrients, to the gas. And so on and so on. The cycle continues up to the present. Behold, our clump has transformed into a galaxy, comprised of many generations of stars, and with some gas still remaining to make more. In fact, in the latest generation, some heavy stars may still be around because they have yet to explode. Let's look in more detail at what we have created. There are 6 important observations that we can make. 1. The gas between the stars is not as it started. It is enriched with nutrients. Witness the color of the water in the jug. 2. The fraction of the system which is in the form of gas has declined as the concentration of nutrients in the gas has risen. That is because of the birth and death of stars during the course of evolution. 3. There are long-lived stars remaining from each generation that formed. Witness the water still remaining in the glasses. 4. Each successive generation of stars is more enriched with nutrients. You can see this from the deepening color of the water in the glasses. The first generation can be recognized by the absence of nutrients. Notice the clear water. 5. Whether I start with a large clump or a small clump, I would come to the same conclusions. The scale of the system doesn't matter. 6. Whether I execute the demonstration quicker or slower, I would come to the same conclusions. Time doesn't matter. What I have just described is the closed box model of galaxy evolution, named so because of the underlying assumption that no matter flows into or out of a galaxy during its life. It does a remarkably good job of sketching out how galaxies or their parts evolve, but it isn't perfect. For example, stars with no nutrients have been sought in the Milky Way, and they appear to be extremely rare. Oops! Does this represent the destruction of a beautiful theory by a single ugly fact? To quote Tarnima Fifi, an award-winning student, there is no such thing as failure, only learning. Maybe the Milky Way was not a closed system. Maybe the Milky Way accreted gas during its lifetime, say by merging with passing clumps or other galaxies even. Lots more stars might have formed in subsequent generations, to the point that nutrient-free stars now represent a tiny proportion of the whole, and thus are hard to find. Or maybe the way that stars have formed has changed with time. For example, if all stars produced in the first generation were heavy, none would have survived to the present day. They would have blown up long ago. Boom! Problem solved. Maybe. Clearly, we need to learn more. That's why we have telescopes. Perhaps you are questioning other aspects of the model. If so, good for you. It means that the model has made you think. While the closed box model may be an oversimplification, it is the beauty of its simplicity that has led us to profound insights into how we came to be. Now that you know how, try making your own galaxy, perhaps using your favorite ingredients. Cheers!